Pre-Calculus Lesson 4.2, Degrees and Radians. In this lesson, we are going to look at several things, but for the first portion of this lesson, we're going to talk a little bit about understanding the unit circle, which you did a little bit in Algebra 2. We're just going to build the foundation for it, not the full unit circle yet. Demonstrate how to convert between degrees and radians, convert an angle measure between degrees and radians, and find coterminal angles given an angle. Those are the learning targets for day one. The vertex of an angle is the common endpoint of two rays. The common endpoint of two rays. The initial side is the starting position of a ray. For what you studied in Algebra 2, this was what we call standard position. Standard position is when the vertex is at the origin and the initial ray is on the positive x-axis. So a standard position, an angle in standard position will have its vertex at the origin and the initial ray, that's this one, on the positive x-axis. So if I were to look at this as having a coordinate plane or sitting on top of a coordinate plane, there's my x-axis, there's my y-axis. My initial ray goes from 0, 0 in a positive direction toward on the x-axis. The terminal side is the ray's position after rotation. All right, we have positive and negative angles. To rotate in a positive angle follows the directions of the quadrants. The quadrants are 1, 2, 3, 4. To get this correct on the ACT, just follow the letter C. But when we look at positive angles, a positive angle travels from the positive x-axis counterclockwise. Those are positive angles. If we go in a clockwise direction, then we're going in a negative direction. We're going in the opposite of the order of the quadrants. So here's an example of an angle that is positive. It has its initial ray on the positive x-axis. It rotates around and stops here. This is a positive angle. Here's an example of a negative angle. It has its initial ray on the positive x-axis. It rotates around clockwise motion. That's a negative direction. All right, we're going to look at the most basic angles on what will be on our unit circle. But we all know that a full circle is 360 degrees. If we split that up by quadrants, by the way, we're also going to look at radians. One full circle equals 360 degrees. So if I start at 0 degrees here and go all the way around, I've gone 360 degrees. That's one full rotation. I can rotate beyond that. I can rotate to 370, or I can do another 360 in addition to the first 360. Could do that in a negative direction as well. We're going to look at if we were rotating in a positive direction, what we would hit as we get a quarter of the way there, 2 quarters, 3 quarters, 4 quarters of the way there. This would be 90 degrees. 180 is half a circle. 270, 3 quarters of the circle, and 360. I want to talk about radians too, just briefly. That'll get it out of the way a little bit first, at least the quadrantal angles. If this is 1 unit, if our radius was 1, then our circle would have a diameter of 2, and the circumference would be 2 pi r, or pi times d, which would be equals 2 pi. The circumference would equal 2 pi. So traveling around this, the distance around the circle would be 2 pi, whatever the units are, inches, centimeters, whatever. Well, I'm not going to go the full, if this is 2 pi units, 0 radians, comma 2 pi units, radians are measured in terms of a percentage of the circumference. That would make this half of 2 pi. I've gone half the circle. I've done half of 2 pi. Well, half of 2 pi is just pi radians. That would make this a quarter of the circle. A quarter, or 2 pi over 4, would give me pi over 2 radians. 3/4 of the full circle being 2 pi over 4 would be, 3 would be 3 pi over 4. So we now at least have our radians for our quadrantal angle. That shouldn't be too new for you. We'll look at the radians of the rest later. We now split this. We're going to look, we did the quarter of the circle. Let's split the circle into thirds. Let's split the circle into thirds, or each, not into thirds. I'm sorry. We're going to split it within the first quadrant into thirds. So if I split this evenly into thirds, for each quadrant, split each quadrant into thirds. This would be 30 degrees because I've rotated up 30 degrees. If I go another 30 degrees, that's 60 degrees. Another 30 is 90. Another 30 is 120. Another 30 is 150, 180. Another 30 is 210. Another 30 would be 240. Another 30 would be 270. Another 30, 300 degrees. One more 30, 330 degrees, and one more 30 brings us right back to 360. We've actually cut it into twelfths. The circle has been cut into twelfths by doing rotations of 30 degrees all the way around the circle. Next, we look at what happens if we cut the quarter of a circle in half. So in other words, we're cutting the circle into eighths. If I did that, this would be 45 degrees. Another 45 is 90. 90 and 45 is 135. Cut this quadrant in half. 180 and 45 is 225. 225 and 45 is 270. 270 and 45, cut this quadrant in half, is 315 degrees. These are the most important circles on our, or important angles on our unit circle. And right now we have all of them in degrees, and we have the quadrantal angles also in radians. If I'm looking at radians, we'll look at radians in class. We'll break down the rest of the unit circle at a later time. Right now, this is just to understand where, if we're rotating in a positive direction, roughly where it would land. I know for a fact everybody should know the quadrantal at the very least, even if you never saw a unit circle before. And if you were in Walled Lake and had Algebra 2, you should have seen a unit circle. But if you don't remember it, or you've never seen it before, you should all know the quadrantal angle. So if I give you an angle of 190 degrees, you should know that since it takes you here to get to 180, you have to go just a little past to get to 190. There are multiple ways to measure angles. 3 of them are degrees, radians, and gradient. You should have discussed gradient a little bit in geometry with some application problems. If you're ever driving out west, they'll often give you the gradient or the grade of the road. If it's very steep, they'll tell you the percentage, the percent grade. But degrees, we're going to be going back and forth between degrees and radians all year, the rest of the year. Degrees are really great in application problems. There's some application problems in surveying. So if you're trying to measure certain angles as you're surveying the land and trying to get things just right as you're building roads or bridges or whatever type of construction you are, sometimes you've seen those people out there with the little tripods measuring different things with them to get the angles right. Surveying and navigation. If we do navigation, we say that we're going 30 degrees southwest, or or 30 degrees east of true north. There's a couple different ways to do that. We'll get into that in a later chapter. We don't usually measure angles when we're doing that type of thing in radians. But there's the downside of degrees is they kind of just randomly picked 360. Well, I shouldn't say randomly. It's not as directly related to the circle as the radians. The radians are directly related to the circumference and a portion or a fraction of the circumference. And if you remember from geometry, angles and arc, not arc length, but arc measure in terms of degrees were the same as long as this was a central angle. Well, that's fine, but it makes a lot more sense with radians because we're looking at a percentage of the circumference. So there is no direct relationship to linear measurements, no direct relationship to linear measurements on the circle. Inches over degrees has no meaning. Inches per degree, oh, I've traveled so many inches per degree, has no meaning. And right now you're going, well, how would it have a meaning? Because for most of you, you've worked primarily in degrees up until now. Some of you did a little bit with radians, but not a ton last year. Radians, assuming theta is the central angle of a circle, but going back to the fact that in geometry, this central angle right here, let's say this was 90 degrees, this arc was also 90 degrees, but then we had to do a separate formula to find the arc length. Well, in radians, this arc length is the same exact measure as the angle, because this is a fraction of the full circle. If the full circle is 2 pi units, then this is pi over 2 units. It is a quarter of the circumference. And so the way we measure angles is with respect to a percentage of the circumference. So theta in radians equals the ratio of intercepted arcs to the radius. So theta in radians equals the ratio of intercepted arcs to the radius. Right now, when we do our unit circle, or when you did your unit circle last year, the radius was 1. So we just looked at the full thing as 2 pi, and so we're looking at a percentage of that. However, if the radius wasn't 1, then the full circle wouldn't be 2 pi. We'd have to have some other calculation. So that calculation is this. Theta equals S divided by R, where S is the length of the arc. So let me show you that on a picture. Here is our central angle theta, here is our radius, and here is S. S is a fraction of the circumference. That divided by R would give you the value of the angle. There is a linear, an understanding of the linear measurement built in. When we have the radian, 1 radian, so if you did S divided by R and you got an answer of 1, that means that S and R are equal. So there's a little bit of background about where radians come from and what radians are. Now let's look at the conversion between radians and degrees, because we're going to be working a lot with both types, and depending on the application problem, we're going to need to be able to go back and forth between them. And we'll also have to be cognizant of that in our calculator. All right, degrees to radians, let's take a look. There is a formula, there are 2 formulas that you will want to be familiar with. If it's something on our unit circle, you should be able to generate it when we redo the unit circle without having to use the formula. So there will be part of the quiz and BA that we have coming up where you will not have a calculator. But for the part where it's not angles on the unit circle, you'll have to have a calculator. And when you do, to convert from degrees to radians, the formula is, well, it's kind of like a conversion factor. If you think back to your chemistry class, if 360 degrees equals 2 pi, well, that could be reduced that 180 degrees equals pi. So really, we have a conversion factor of 180 degrees equals pi. So if I'm starting with an angle in degrees, so I have x degrees, to convert that, I'm going to have to divide by degrees and multiply by radians. Oh, by the way, that's pi radians. So I will have to take my x degrees and multiply by pi radians divided by 180 degrees. Then my degrees will cancel out and I will have my answer in radians. If I need to convert from radians to degrees, then I will start with my angle in x radians, and I will multiply it by 180 degrees over pi radians. This will cancel out the units of radians and convert it to degrees. So write each, and we need to do this in fraction form as well, especially when it's in radians. I do not want a decimal answer. I want it in fraction form. So here we have 120 degrees. To convert from degrees to radians, I have to remember that the conversion factor is pi radians over 180 degrees. 180 and 120 are both divisible by 60. If you divide that, you get 2/3, but you could also put it in your calculator since you're going to have a calculator for this for now. 120 over 180 is 2/3. So this becomes 2 pi over 3 radians. And you don't have to write the word radians. If I don't see a degree symbol, then the assumption is that your answer is in radians. So make sure that if you're answering in degrees, you give me a degree symbol. Negative 45 degrees multiplied by pi over 180, it's still going to be negative. 45 goes into 184 times, so this reduces to negative 1/4 pi, or negative pi over 4. And 5 pi over 6. Now we're converting from radians to degrees. So we need to multiply this by degrees, 180 degrees, over pi radians. What's happening here is the pi's are canceling out along with the radians, and we're left with 5 times 180 over 6, which is 150 degrees. Take a moment to try that for letters D, E, and F. You can pause the video and try this for D, E, and F. If you did this for letter D, you should have gotten 270 degrees, because 3 pi over 2 times 180 divided by pi, the pi units cancel. 3 times 180 over 2 is 270. Negative 60 degrees out of 180, that is negative 1/3, so this is negative pi over 3. How did I get that? Negative 60 degrees times pi over 180. I reduced the 60 over 180 to 1/3, and I have pi still. And lastly, negative pi over 4 should have been negative 45 degrees. Again, this is negative pi over 4 times 180 divided by pi. The pi units cancel. 180 over 4 is 45 degrees. It was a negative angle. Coterminal angles are angles that have the same initial and terminal rays. But that means that they are 360, at least 360 degrees apart, or some multiple of 360 degrees, or in terms of radians, 2 pi radians, at least 2 pi, or some multiple of 2 pi radians apart. So here's a positive angle, and here is a negative angle that have the same initial and terminal ray. So those are coterminal. I could also spin around this many times and land at the same spot, either in a positive or in a negative direction, and I would still have a coterminal angle. So we have a formula to calculate this, where we're going to use alpha as our angle. In degrees, they can be calculated the following way. our angle plus 360 degrees times n, where n is an element of the integers, where n is an integer. That's this number set notation for integers. That means that I can take 360 and multiply it by 1, 2, 3, 4, or 0, -1, -2, -3, -4, to infinity by the counting positive and negative numbers. And it would still be, if I add that value to our original angle, it would still have the same initial and terminal ray. In terms of radians, this would be alpha plus, well, going full circle in radians is 2 pi units. So it'd be 2 pi n, again, where n is an element of the integers. So let's take a look. We're asked to identify all angles that are coterminal with the given angle, then find and draw one positive and one negative angle coterminal with the given angle. So find all angles? That means we're going to be using this notation, because I don't want to sit here all day, I don't think you do either, generating an infinite number of angles. We'd run out of space on our paper, and we'd never do it. So let's go through this real quick. For 60 degrees, because it's in degrees, the notation for all would be 60 plus 360 degrees times n, where n is an element of the integers. For a positive coterminal, I would simply do 60 plus 360, which is 420, and 60 minus 360, which is -300. If on my first attempt at addition and subtraction of 360, I did not get the positive or get the negative, then I would continue adding or subtracting 360 until I got one that was positive and one that was negative. For 3 pi over 4, the formula for all would be 3 pi over 4 plus 2 pi n, where n is an element of the integers. Now here's where we have to add 2 pi to this. So I've got 3/4 pi. In terms of fourths, 2 is really 8/4. So that's going to be 11 pi over 4 will be coterminal. If you're not confident in that, you can always convert it to degrees and double check. And I also have to subtract. I've got 3/4 pi minus 8/4 pi. If I don't get a negative right away, I will in this case, then I'd have to keep subtracting 8/4 pi until I actually did get a negative. So there's my positive angle. Here will be -5/4 pi. You can write it as -5 pi over 4 or -5/4 pi. For -30 degrees, we're going to write the formula -30 degrees plus 360 degrees times n, where n is an element of the integers. -30 plus 360 is 330 degrees. -30 minus 360 is -390 degrees. For -pi over 4, again, since it's in terms of fourths, 2 pi would be 8 pi over 4. So I'll have to do -pi over 4 plus or minus 8 pi over 4 to get my two answers, my positive and my negative. But for my answer for all, -pi over 4 plus 2 pi n, where n is an element of the integers, gives me all possibilities. I'm just asked to list one positive, one negative. -1 and 8 is 7 pi over 4 for my positive. -1 minus 8 is -9 pi over 4 for my negative angle. I just double checked. We do have one last learning target for this lesson, and that is to talk about arc length. Arc length, because whenever you do arc length, you had a crazy formula where you had to multiply by the radius and do all this stuff when it was in degrees. Whenever you do arc length, you need to make sure you convert to radians first if you are in degrees, so that we can follow the correct formula. The formula when theta is in radians is that S, which is the arc length, equals R times theta. This will make sense because if you remember that in terms of radians, the angle theta is really the arc length divided by the radius. We talked about this on the front page. It's that little arc length divided by the radius. It's a fraction of, it's a fraction where r is the denominator. If you multiply by r, you're going to get the arc length right back. So arc length is the radius times the angle, but the angle must be in radians or it doesn't work. So here we are asked to find the length of the intercepted arc in a circle with the given central angle measure and radius. Round to the nearest tenth. This angle is already given in radians, so we don't have to convert it. So to find the arc length, if I were looking at 2 pi over 3, which I could look at where that is on the circle, but right now I'm just going to follow the formula. We have r times theta, so I have 2 times 2 pi over 3, which is simply 4 pi over 3 would be the arc length, which in terms of a decimal, normally we answer in a fraction, but because they asked us to round to the nearest tenth, we're going to do 4 pi over 3 in our calculator. This is roughly 4.1887, but rounded to the nearest tenth, 4.2 meters. Our radius was in meters, so the arc length will also be in meters. For letter B, this formula would be great, except 135 is not in radians, so we have to convert it to radians first. 135 times pi over 180, 135 over 180, convert it to a fraction, that's going to be 3/4. This is 3 pi over 4. But that's just our angle. To find the arc length, we have to do 0.5 feet times 3 pi over 4. Since we are asked to round to the nearest tenth, normally I would have done 1/2 times 3 pi over 4, which would be 3 pi over 8. But we were told to just round to the nearest tenth, so I would just put it in my calculator at once. 0.5 times 3/4 times pi, or times 3 pi over 4, however you want to do it, is 1.17, which would be 1.2 feet for the arc length for 3/4 of that circle if the radius is 0.5. All right, 3/4 pi, not 3/4. All right, this concludes the first day of lesson 4.2. Being able to convert between degrees and radians, being able to find coterminal angles, and being able to find arc length. We'll look at sector area and angular momentum in the next lesson. Have a great day.